Hello, I hope I'm audible. So last class we discuss tool, okay, where we discuss ID versus VGS, okay, and with this key how you can simulate it. So today I am going for further, okay. Today we will discuss some more important point in the tool so that you can analyze more accurately, okay. So today we will design one more that circuit that we will talk about ID versus VDS. So let's start with that key. Okay, so firstly you invoke that license. You just go for your terminal. Okay, in this terminal I am just going for CD documents. Okay, it may be different in your system. Okay, it depends on installation process. Okay, okay, and just I am commanding some line and just virtuoso. Okay, so here virtuoso cadence virtuoso will active, and here this is command interpreter window. Okay, this is a central hub of the cadence. Everything it is showing, okay, that message, error, warning, okay, command, what are you doing in this, everything it is showing at the command interpreter window. Okay, so as we know that we go for tools and library manager. In this library manager you have a set of library that will be available in your cds.lib. In a cds.lib you every library have a path, and this library, if the cds library have a path, then only you can find this library on this cadence tool. Okay, if any library, if you want add any library, you just simply paste it, okay, and write the path in a cds.lib of that file, and that file will be come here. Okay, so last class we designed one library that name is analog circuit live. In the analog circuit live we work on the NMOS characteristics, and where that we have a schematic. In this schematic you have this type of circuit. If you press F for fit screen, okay, so last class we discussed that you have a this is a gate to source voltage, because that gate is have a voltage of VDC, that is 650 millivolt, and where that you have a source is grounded, so VGS is 650 millivolt, and you have a VDS that is 300 millivolt, and the width is variable. So how the graph, so just revise this, what will happen. So just go for launch, firstly check and save, okay, and just go for launch. Okay, ADE Explorer, you can go for ADE assembler also, Explorer also, you have a two path. I am just going for create new. Okay, and this is a maestro. Okay, it will generate a maestro. In a previous cadence version, that is represented the ADL window, that is analog design environment L. Now it is talking about the ADE assembler or explorer. Okay, so they both are same. Okay, that this is a just advanced version of that. Okay, so you can go for analysis, you can click on that add analysis, you can go for DC AC transient as per the requirement. Here I am just sweeping the gate voltage, so you can save the DC operating point. This operating point set means as per providing the DC voltage in the circuit, at that point what is your value, what is the value of region, what is the value of current, everything it represent on that given value. Okay, so component parameter, select component. Okay, I am just sweeping this gate voltage, just go for this. Okay, and here you have a V1 is sweeping, and the DC voltage of that is sweeping, and let I am sweeping from 0 to 1.2. Okay, so this is 0 to 1.2 volt. Okay, you can make that step size that 0.01, or automatically it depends on you. Press OK. So the DC analysis is done, that DC analysis part is done. Okay, you set that one variable in the circuit, so just click on the variable, press. Okay, that variable name was X, so you can put it, okay, that X, and you put that what is the width, you let that 0.5 micro, I want that 0.5 micro, you can set it, press OK. So the X is 0.5 micro. What you want to take the output, where you want to output that output to be saved from the select on the design, and let I am trying to find out what is the drain current on the basis of VGS. I am not taking the VGS, I am just introduce this. Okay, I want the plot. Just click on this and just run it. So you will find it okay, that graph is like this. Okay, so it is running. Okay, the plot is like this. Okay, so this is NMOS drain current with respect of VGS. You can change the width also. Okay, so this is the DC voltage is sweeping on x-axis, that is VGS, and this is your drain current, that is y-axis, this is ID, that V as per the VGS is moving on, as per that ID is representing. Okay, so Cadence have a variety, it will showing that ID versus VGS, but Cadence have a lot of thing. It depends on your requirement. If you want that simple graph, there is no any requirement of, okay, on this platform you can check it ki ID versus VGS graph is showing, but that region and VTH, everything is showing on that exact operating point. Must just think in a way, I am just representing like this. Okay, you have a that this is the circuit. Okay, let I am designing, I am going for a circuit. Okay, this is the circuit. In the circuit you have a 650, 300, this the value of the DC operating point. Okay, that will show if you go for that results and print and DC operating point, and you click on this, it will showing that all these value, but this value is only valid for 650 millivolt for gate voltage and 300 millivolt for drain voltage. You can check it, the drain to source VGS is 650 millivolt and VDS is 300 millivolt, means everything is showing at for particular value. Okay, if you want that region is also specified for the different for this v value. Okay, you can go for region. Okay, that where is the region, this is the region, the region is 2, that VDS is greater than VGS minus VT, because VGS is 650 and VTH is 500 approx, that is what is VTH is 614.65. Okay, so that's why that VGS greater than VTH and that VDS is greater than VGS minus VTS. That's why this is your MOSFET in saturation region. But if you want key, okay, every VGS value, what is the region, what is that CGD, what is the CDS, what is your VTH, if you want in such a way key, okay, every value of the VGS, what is that, just like the graph is showing that ID versus VGS, it is showing like the, or every value of VGS, what is the ID, but here you are not representing what is the region for different value of VGS, what is the value of VTH of different of VGS. If you want in such a way, you can use some extra part in Cadence. What can you do? Just I am representing here. Oh, sorry. Okay, so this is the way. Okay, so I am just going for taking one file, where that file it will store all the data, but Cadence depends on what you want as a output. If you want that lot of analysis, you must specify or command to Cadence कि okay, I want every value on the variation of the VGS. Here is the only variation of ID with respect of VGS, but if you want lot of value, means if you want all the value of the DC with respect of VGS, you require some such function. Just you go for one file name that I am just representing in a way कि okay, let I am I have a one file. Okay, just I am going for analog circuit live. You can go everywhere, anywhere for the folder. Okay, I am just writing that I am invoking that terminal. Okay, that this is a terminal, and if you know as a basic command that you are using a empty file for touch. Okay, we are using command touch to touch touch, and let I am designing that file name is, that is abc.scs. The name can be anything, that it can be Vivek, it can be Pine, it can be Vaibhav, it can be anyone, but the extension is scs.scs. Okay, so that scs is important, that so by the touch, that this will be showing that abc.scs file on that, and this that is empty file. Okay, so if you just enter it, you find that okay, you have a file is abc.scs. This is an empty file. If you open it, you find that this is a abc file. Okay, so I want to all the file, all the data here. Okay, so what can you do? You simply check it where it is your, what is the name of your that is nm0. Okay, just a minute. uh, that is the name of nm0. Okay, the MOSFET name in nm0. Let you have a name is nm1, nm2, nm3. Okay, what you want? You want that nm0, all that value of nm0 you will want to save on the basis of VGS variation. You just go for nm, that you write the command here. Okay, or a one line, that is save. I think that file name is save, that is nm0 colon all. Okay, so if that MOSFET name is nm1, you write is save nm1. If that PMOS, you write the save pm0. It depends on nm0, nm1, nm2, that is the MOSFET name. Okay, so that MOSFET name is nm0, so you are writing nm0. Why? Because this is showing that this is nm0. Okay, the name is nm0, so that's why I am writing here save nm0 all, and you save it. Okay, and if you save it, just save. After that save, just that cancel out. Okay, so this file is present in your in your file, that is analog underscore circuit underscore live. So this is the basic thing. Okay, so what you change here, you can go for Maestro. Okay, here you have a setup. So in the setup, you can go for simulation file. Okay, so if you want to all the data, just region, CGS, CDS, VTH, everything you want on the variation of the VTH, on the basis of the VGS, what will happen of the different value. Okay, you just check that DC print value is showing for particular VGS and particular VDS. But if you want all that such value, just like ID and just like ID, if you want all these value, you can go for simulation file. In the simulation file, you have a definition file. In the definition file, you can save that file. That name is what, that abc.scs. Okay, that name is abc.scs. You just open it and apply and okay. So this file is saved. So basically this file store all the data. Okay, and just run it. Okay, just run after that. So if you run it, so this is working. Okay, there is nothing, I am not doing anything change on the circuit. I am just entering one file. That file is abc.scs. that will be help to all storing the all the data. So this is showing that okay, that ID versus VGS. If you're going for classic to browser, so if you go for DC, if you go for the DC, that you have a lot of values here, means all the plots is present here. Previously you have a only ID versus VGS graph. There is no any value of that region, there is no plot of the region, there is only representation of that particular operating point. But now you can check it. Okay, that let I am going for region and click on this, it is showing the plot by that by the help of this that .scs. So if you are looking this plot, you can check it. This is region 0, this is region 3, that is subthreshold, this is cutoff, this is subthreshold, this is saturation, and this is linear. Okay, You can give that name also. Go for graph and read add label. Okay, and you can like write a reason. Uh, okay, you can write it reason equal to 0. Okay, this is region 0. You can copy it and paste it here. So this is region 3. You can. Okay, this is region 2. Okay, so you can go for that, and this is uh, region 1. Okay, you can check it. Okay, so this is region 0, that is cutoff region. Okay, and you can check it after that. Once VGS is near about VTH, that is region 3. After that VTH, when that VGS is greater than VTH and VDS is greater than VGS minus VTH, it will be enter in a saturation. And once that VGS is going on and VGS is higher, as much higher, then VDS is not that much enough to greater than VGS minus VTH, so MOSFET enter in a linear region. So this is showing as a linear region. So region 1 is a linear, region 2 is a saturation, region 3 is a subthreshold, and region 0 is cutoff. So this is cutoff, there the current is 0, nearly about 0 current. And this is region 3, where you find that the current is nanoampere. In saturation region, you find that current in microampere. And after that, this is a square term, that is square law. That is ID is directly proportional to VGS minus VTH ka whole square. So that's why it is showing the parabola. And after that value, it is showing a linear, that ID is directly proportional to VGS minus VTH. There is no any that is square term. This is just like y is equal to mx. Okay. So you can check, okay, that not only VGS and not only region, you can check that VTH also. If you want that, what will be the effect of VTH as per VGS is changing, you can check it that VTH is not change as per VGS is changing. VTH is always constant at 614 millivolt. Okay, it depends. Okay, you can go for transconductance. Okay, that gm is very important point once you go for the amplifier, or lot of thing is required. Okay, so that is gain part of that. So the gm, you can check that gm, what is the plot of the gm. So this is the plot of gm. Okay, so as per gm, that here that it is in a cutoff or in a sub threshold, that gm is very small. But if you talk about saturation region, the GM is very high. But if you talk about linear, GM will reduce. That's why we are talking about GM is taking in a higher saturation region. Because in a saturation region, you find that higher GM. The transconductance is high. But if you talk about linear region, GM is small. GM is dou ID by dou VGS. Okay. So if you talk that ID is directly equal to VGS minus VTH, if you differentiate ID by VGS, you will find the lesser value of transconductance as compared to ID is directly equal to VGS minus VTH ka whole square, and you differentiate it, you will find that GM is higher. Okay, so you can check it that GM is here. Okay, so as you can check it also that here it is ID, here it is GM, here you have a region, you can check the VTH. In a previous case, in a last class, we check all that value only at that point. What is that point? That VGS of the 650 millivolt and VDS on the 300 millivolt or 500 millivolt. But after that file, you commanding that key every simulation, every point you want as the variation of VGS. If you want everything from the Cadence, you put some such of file. Of course, Cadence will take the memory from that your CPU and from this your SSD, and it will simulate it. But Cadence will not provide every value if you not providing the command. So Cadence is very intelligent. Okay, if you want such a particular value, so it will give the such particular value. If you want large of value, of course you will put the some library files or files that it will show the all that values. Okay, okay, here it is. You can check that, okay, that gm over id. Okay, we if you talk about gm over id, here it is also gm over id also. Okay, so you have lot of things. Okay, okay, so I am just representing here. Okay, so GM over ID. Okay, you can click on the GM over ID. This is GM over ID plot. Okay, so GM over ID, on the basis of that you can design your circuit. Okay, we have a two way to design your analog circuit by the help of by the variation of iteration of the W by L on that supply, or you can design your amplifier or current mirror or any op-amp circuit by the help of GM over ID. Okay, so we have a different method to design your circuit, and gm over id is as much good as compared to that basic vgs greater than voltage. Okay, so okay, you can check that lot of thing you have. Everything is defining with respect of vgs. As per vgs is changing, you have a lot of thing you can. Okay, of course that cadence have a lot of thing you can. Here you have only vgs is varying. You can check in such a way कि okay, on the variation of id what will be the graph. Okay, you can, okay, that is lot of thing it happen in a cadence. Okay, you can make any one of that x-axis, anyone make a y-axis. You can design as a command. Okay, but now for a starting purpose I am giving some idea. So here you can check it that as here that vgs is changing, and you can plot every value. Okay, so that here it is that r out. Okay, r on, r out. Okay, if you want r out, you can check that r out. Okay, r out is this. Okay, you want r on, you can go for r on. So this is r on. Okay, so you have, okay, you have a lot of value. So what is the process? Just simply what it do, you simply want okay, you make a one touch file, that empty file, that name is touch, touch. You are providing command on that your on any library you can use, any folder, any directory you use. In the directory you write that touch command, open the terminal, touch command, and write the name of anything, let x y z a b c anything, and that the extension is important at .scs. If you write that .scs, means you are uh, forcing that okay, this file will be helpful for simulation. Okay, and .scs, and you write the command that save nm0 colon all, and if this is nm1, so write it nm0, maybe since they at it m0 only. Okay, if this m0 only, so write it save m0. If it is nm0, so I am writing nm0. Okay, and you just save it and just simulate it. If you plot that in the plot of the browser, you will find that you can find that every value of that vgs variation. Okay, so region is important, gm over id important, gm is important, r on or r out is important. Okay, that's why I am showing all that value. Okay, and that maybe the transient frequency, and you go for that. Okay, okay, what is the frequency of the MOSFET? Okay, so I am not going for the transient frequency or cgg. Okay, so for now you have a basic knowledge of the cadence. Okay, okay, you can simulate the circuit in such a way that on that platform you can check all that value of the region, of that value of VTH, on the value of that R on, R off, everything you can check. Okay, at the variation of the VGS. Okay, so this is the basic part. Let's talk about ID versus VDS. Okay, and you can also figure out what will be the different width. Okay, you can put the different width, and you can find it. Okay, okay, let's try it. Okay, let's try this. Okay, if you want, I can. Okay, so that width is x is 0.5 micro, make it 1 micro. Okay, so there is 0.5 micro, 1 micro, you have a 2 width. On the basis of 2 width, what will be the plot? Just you can check it. That on the basis of that, what will be the plot? So just it is taking some time because it is simulating all these fundas of that simulation. Okay, so it is showing that okay, this is that if you open it, okay, this is nm0 for 500 nano means 0.5 micro, and this is for 1 micro. Okay, and if you want to browse it here, and you can click on the DC, you can find it. Okay, you have a region or lot of thing. So there is two region on the basis of different width. You can check it. Okay, okay, you can make your idea also. At 500 nano, you find that region is saturation region is higher, means it is shifting right. Okay, that region is higher as compared to 1 micro. Okay, that 1 micro region is lesser, means if you are finding that okay, this is that is, let this is a, okay, this is a point and this is b point. So you find that the dx is 420 millivolt. Okay, this is the difference. Okay, so a to b you have a difference of 420 millivolt. Okay, and if you want that by the help of 500 nano, you can check it. Okay, this is uh, a here and this is b here, and you find that this is 430 millivolt, that the difference is 10 millivolt. If you using a 500 nano, you are finding that 10 millivolt is higher in saturation region as compared to 1 micro. In 1 micro, your MOSFET is entering in a linear region is fastly. Why? Because current is heavy, ID is heavy if you are using that higher width. If you are using a higher width, that current will be high, MOSFET is fastly going to the linear region. If you are using the lesser width, the MOSFET have a higher, that it will maintain higher region of saturation, and it is maintain higher voltage for saturation. After that it will be okay. So this is the way you can analyze. But basically, if you know that ID versus VGS graph, if you know the region of operation, if you good in understanding of node voltage and what is the gate voltage, okay, what is happening on the gate side, okay, so that will help you. If you go for that basic current mirror or common source amplifier or differential amplifier, everywhere I am using this only. Okay, we can work all the basic. Okay, we will discuss all these differential pair, current mirror or common source amplifier or any amplifier on the basis of ID versus VGS only. ID versus VDS only. If you are good in ID versus VGS, ID versus VDS, and you are good in understanding of that value, so you can very easily design your specification meet. Okay. So this is the way. Okay, you can go for that different thing. Okay, this is the region. Okay, region is very important. That's why I am showing always. And because if you have a MOSFET have a region. If you are analog circuit designer, you must have a understanding of the region. Okay, let's talk about GM. You can go for GM also. So you can check it. Okay, I am just removing this region or something. Okay, just close it and just check that region. Okay, if you are using at 500 nano, the transconductance is small. Okay, if you are using that 1 micro, that GM is high. Why? Because current is high. GM is directly proportional to I. GM is equal to 2 ID upon VGS minus VTH. Okay, that lot of formula you have. GM is equal to mu n CUXW by L VGS minus VTH. Okay, the under root 2 mu n CUXW by L ID. Okay, so as per the requirement of that you can use any one of that formula. So GM is present here. I can check it ki okay, GM is changing. If you are using a 500 nano, the GM is higher. GM value is what? That if you press V, you can check it. Okay, that this is very high value, that 378 microsiemens, where that if you are using a 1 micro, this is near about double. It is near about double, that is 730. Okay, this is 730 microsiemens. So GM is high as per the current will high. But of course, if you are using the higher width, of course you will have a problem of saturation region. Okay, so anything, if you are finding something, you will give some your time. Okay, if you are if you are finding that good results by the help of GM, okay, so of course you find that, okay, one of that compensation is present, that is saturation region. Okay, so region is small, means that in by the help of 5 micro you find that region is 430 millivolt, that is difference. And if you talk about 1 micro, it have a 420 millivolt. Okay, so you can just think in a such a way. Okay, so that GM is what, that GM is here that 378 microsiemens, and here it is 730 microsiemens. As per here it is, this is 1 micro and this is 500 nano. If you are not looking properly, so I can make it extra thick. Okay, so you can uh, understand properly. Okay, so this is okay, so you can check it. Okay, so on the 929 millivolt of the VGS, you find that higher transconductance, that is 730 and 378. Okay, so if you are designing a common source amplifier, you can think in a way ki, okay, on that that VGS is 929, you find this. So as per this, what is the drain to source voltage? Okay, what is VDD minus IDRD? So this is the way. Okay, so you can, okay, you can check it. Okay, so this is for what, this is for 1 micro and this is for 500 micro, 500 nano. Okay, 0.5 micro. So that is the analogy. Okay, of course cadence will help you to analyze, but firstly you will go for with the pen and paper. At least you can understand what will happen. Okay, that simulation always give the result. If you are not good in understanding of that concept of the MOSFET, so just a result, just you find the waveform. Okay, and you can't find anything from that. Okay, if you are good in concept, if you are good in understanding of that, okay, this is happening by this is happening due to this is happening due to this. Okay, so you can make your own idea. Okay, that's why analog circuit designer is required in VLSI industry. Okay, you can check the VTH also. That the parameter is important. That VGS, okay, that parameter is what important. That okay, what will be the region, what will be the GM. Okay, these are the parameters that is very important. So if you talk about 500 nano, so that's 614 millivolt. And if you talk about 1, that is 617. So don't think in a way that is lot of change, that is a 3 millivolt change. That if you are changing the width that you will find the a very small change of that, or you can say that VTH is not changing as enough. VTH is mostly depends on source to body. If you are changing the width, at lower width you find that lesser VTH. If you are using higher width, that is providing that 617 millivolt, that is the change of 3 millivolt. That don't think too much about it. You can think that ideal VTH is constant, and VTH is for 500 nano, it is 640. So it will be same for 1 micro also. Okay, so VTH is constant. That ID and GM will be a drastical change. That what is the drastical change? That you can check it at same value of that, of same value of this 929. It will be providing that GM is 378 and here is 730. That is a double change. Okay, so that is important. Okay, the transconductance is important. If you talk about current at 500 nanoampere, you find the 97 microampere current. But if you talk about 1 micro, it is nearly about double, that is 185. Of course 97 is 500, and if you are using a double width, so you can use a double current, that is 184 or 185 microampere. Okay, so this is the way. Okay, so let's talk about, okay, another thing. So this is ID versus VGS. Let's talk about ID versus VDS. So here I am just changing that ki, okay, that VGS is 650 millivolt. I am just changing V2. Okay, here in a previous case I am wearing that VGS and checking about that ID. Now I am going for VDS is changing where that VGS is fixed. Okay, so you can go for that key. Okay, that DC is present. Here I am not using VGS is varying. I want VDS is varying. That name is V2. I am just writing that name is component name is V2. Okay, or you can select component and select that and put that value, or you can write it. Okay, simply V2. So V2 is your voltage of VDS, okay, and you want it, okay, what will be the ID with respect of VDS, okay, where that VGS is fixed, okay, so just run it, okay, and you will find it, okay, what will be happen with the help of different width, okay, you have a two width that 0.5 and 1 micro, you can check it, ID versus VDS graph. Okay, it is net listing, it is taking some time because it is simulating all these parameters. Okay, so you can check it, okay, that current is id versus like this id versus why it is looking that too much slope, because that length is very small, that is nearly about 45, that is minimum length you have, and as you know that length is small, that means resistance is lower, and the slope is defining id versus vds means what, that id upon vds is what your gds, yeah, 1 upon r naught, okay, and r naught is 1 upon lambda id, okay, you can figure out, okay, so we will discuss once we go for the common source amplifier, but till now I am just representing here that it is showing the lot of slope here, as you know that as per that vds is changing, your id is changing a lot of things, and if the MOSFET is a voltage controlled current source, MOSFET is a voltage controlled current source and it is behave like a current source, so there is not, after the saturation region it will be not showing that effect, okay, so there is lot of slope is present, so what can you do, okay, I am just changing here, okay, that length here, okay, so that is the nmol, the length is 45 nano, make it 0.5 micro, means I am just using that width is 0.5 micro, that is higher width, okay, I am using a higher width, sorry, higher length. If you are using a higher length, of course you have a higher resistance, because r is equal to rho l upon a. If the length is higher, so resistance will higher. If the resistance is higher, so 1 upon r naught, that is a slope of id upon vds, it will be lower, okay, so as per the resistance will be higher, that at once your what, that your slope will be reduced, okay, so that's why, okay, I am not using any resistance, I am just controlling with the help of length, and that's why that channel length modulation effect you can reduce by the higher length, okay, so that's why in an analog circuit design we are using a higher length. If you are going for a lower length, if you are going for 45 or 22 nanometer and lower than that, so you will find lot of effect of short channel effect, sorry, second order effect, okay, it may be channel length modulation, velocity saturation, DIBL, drain induced barrier loading, gate induced drain leakage, lot of second order effect, body effect, okay, that will introduce if you are using a lesser, that channel length is small, okay. So I am using a higher channel length so that output impedance is higher. If the output impedance is higher, the slope will be reduced. So I am using just a higher length and a 500 nano, okay, and just simulate this, okay. Okay, and if you are changing anything in your circuit now, if you are changing anything, let I am changing the length from 450 nanometer to 500 nano, so of course after the change you just go for check and save. Without check and save, you simulate it, it will showing some error or warning, okay, you are not saving, so just save and save. After the changing of that circuit, just save it and go for simulation. Okay, you can go for simulation, it is taking some time pending, okay, it is waiting, please wait for that. After that it will check all these parameters and then it will net listing and it will provide, okay, so if you are looking from previous one to this one, that slope is lesser, okay, that slope in a previous case it is too much slope was present, but if you are using a higher length, that slope is lesser. Basically what is the current source, the current source is what, that current source in a saturation region, MOSFET behave like a current source. Means if you are changing your current source, means that current source can take any voltage across it, but the current is constant towards the load. The voltage can be anything, but the current will be constant to the load. So I am just representing it. Ideally it is just constant, okay, just make it constant. If you are changing that length is higher, or you are using that extra resistance over the cascade of that, okay, let you are using a higher resistance over the MOSFET, so of course the resistance will increases, so your output impedance will increase, and the slope will be near about what zero if that output impedance is higher. So you can check it, okay. So this is the way I am just changing that length, and you will find that slope is lesser than previous one. So this is the graph, okay, you can check it, okay. It is depends, okay, your understanding. Okay, so the lower length will be problem for you, okay, if you are using a current mirror, if you are trying to make it you're using a that amplifier, okay. So you can't too much control your id drain current as per your vds, okay. Here you can, there is not that much changes, okay, that the current is in limited amount, okay. You can make it more accurate as per that resistance increases. So this is this is for uh, 500 nano. If you are using a 500 nano, the current is that much. If you are talking about the current is what, that is 11 micro, okay, that is 11 micro or near about 12 micro, okay, to 11 to 12, okay. And if you talk about 1 micro, if you are using the width is 1 micro, the current is 20 micro, okay. So as per width you are increasing, you will find that your current, okay, that current will be increases as your higher width, as per your higher width, okay. And you can check that your region also. Here you can check the region. You can dc, of course we have a simulation file and everything is same for us, so you can check the region also. You can check the region here. So I am just checking, okay, for let for 500 nano, I am just checking for 500 nano. So this is region 0, sorry, region 1, this is region 1, and this is showing for region 2, okay. So this is a linear region, this is showing for linear region, and this is for saturation region, that after that vgs minus vth, it is showing the saturation region. Vds, the overdrive voltage is that much 0.25. After the 0.25, it is showing the saturation region. So this is a saturation region and this is a linear region. If you talk about 1 micro, okay, I am not going for, if you are talking about 1 micro, so that your region is like this, okay, this is the region, and that after that it will be in saturation. So if you are comparing both that, so if 500 nano you are talking about, the saturation, the linear region is wider as compared to 1 micro. If you are talking about 500 nano, so that your region is linear region is wider as compared to that 1 micro, okay. So you can, okay, you can check it, okay, in such a way, or you can press a here, okay, what will be that a here and a here, b here, sorry. So you can find it, this is 250 millivolt, okay, and this is, okay, you can check it a here, and this is b here, this is 240 millivolt, that will be a 10 millivolt changes there, yes or no, hello. So as per id versus vgs, you find that key what will happen, here it is also, you can check it, okay. Okay, so you can, okay, so simply you can analyze as per your understanding what is happening, okay. If you are changing that width, what will be, okay, this is a linear region, this is a saturation region, okay, that is a slope is here, how can we reduce that slope, okay. So it depends on you, okay. You can reduce that slope also by the help of adding the cascade structure of that, Okay, if you are using a cascade structure, so cascode structure, not cascade, cascode structure, so that output impedance will be high and it will be not showing that much amount of slope. Okay, so this is the way. Okay, you can check that GM also, it is GM. Okay, so this is GM also. So GM for 500 nano, this is the GM. Okay, if you talk about this, so GM is like this. Okay, so GM is different for 500 nano and 1 micro. Of course, GM will be high as per looking in a previous case ID versus VGA. GM was lower for 500 nano, GM is higher for 1 micro. Similarly, the transconductance GM will be higher for 1 micro with ID versus VDS, and ID versus VGS is lower. Okay, so you can. Okay, and of course we discuss in a GM will be lower in a linear region and higher in a saturation region. You can check it also that GM is lower in a linear region and in higher in a saturation region. That's why we are talking about saturation region. We always talk about why that MOSFET in a saturation region. If you talk about MOSFET in a saturation region, you will find that high transconductance. Okay, so that will be directly related your gain. Okay, always if you are finding the gain, that gain of the common source amplifier is minus GM R not parallel of RD, or you are talking about differential amplifier, that is GM1 plus GM2 are not parallel, something like that. If you are using a op amp or inverter, anything, if you are using, that transconductance is directly related with the gain. So that's why the transconductance is important. So that's why we are talking about the saturation region. MOSFET in a saturation region. If the MOSFET in a higher saturation region, you will find that higher transconductance. But if you use the MOSFET in a linear region or cutoff region, that transconductance is very, very small. Okay, so always we try to make that MOSFET in saturation. So this is the ID versus VDS. Okay, so here I am changing that width. Let I am changing the different VGS on that. What will be that ID with respect of VDS. Okay, so we have a lot of things. We can simulate a lot of things. But if you are good in basic characteristics now, if you are good in characteristics, you can analyze your output in terms of waveform. Okay, just like simple, if you are good in solid state, in a solid state, if you are good in energy Fermi level, so you can design everything, you can understand everything in terms of Fermi level. Or you can, if you are good in network or RC, you can analyze your circuit, like it may be a VCO, it may be a ring oscillator, it may be a CMOS inverter, it may be a schematic trigger, it may be a PLL, it may be a DAC, it may be ADC. Anything you have, you can compare from that basic network. The whole analog circuit, it depends on two basic fundamental, that is network and RC. Okay, so if you are good in network and RC, you can analyze. And the third part is basic characteristic of ID versus VGS, ID versus VDS. What will happen by the help of W by L? What will be happen of the variation of the node voltage? Okay, so that is the basic requirement. You must work on it. Okay, if you have a cadence, so go for that cadence. If you are not have a cadence, go for LT spice. LT spice also have a MOSFET. Okay, you can go for analog circuit in a LT spice, just Google it, and you can take that is 65 nanometer technology. Okay, and you can work it. Okay, so that LT spice also very good for open source, and if you have a cadence, so that is very good for you. Okay, okay, let's talk about okay, so now I am checking that, okay, that width is common, that I am taking that width is 0.5 micro, or I can, okay, that the circuit in such a way ki, okay, the width is 0.5 micro, make it 1 micro. Okay, make it 1 micro. Okay, okay, I am not going for fingering and multiplier. We will discuss finger and multiplier as in a cadence, in a layout. Okay, once we start a multiplier, or if the requirement of higher width, okay, so we can. Okay, so what is the use of finger, what is the use of multiplier, we will discuss once you go for layout, or we go for current mirror. Okay, and that's it, that we are using that here it is 1 micro and width and length is 500 nano, and I am changing the VGS, so I am giving that game name is X here there. Okay, I am giving that X volt. Okay, so I want different ID versus VDS graph with respect of different VGS. Okay, so let's check it what will be happen. Okay, after changing of that circuit, you just check and save, go for check and save, and you go for maestro. And here I am putting that, okay, that X is what X is, make it anything, let 0.5 volt, 0.3 volt, 0.5 volt, it depends on you. Okay, so I am writing 0.5 volt, uh, 0.8 volt, 0.5, not writing that 0.5, 0.8. Okay, that don't write that what unit. So 0.5, 0.8, 1 volt, okay, 1.2, okay, it's up to you, 0. Okay, so on the different VGS, what is, okay, let's start with a 0 also, if you are interested, from 0.2, okay, 0.2, 0.5, 0.8, 1 or 1.2, you have a different voltage of the gate to source voltage. On the basis of that, what will be your current? Okay, so just run it and check it what will be the drain current with respect of VDS, where that different VGS is 0.2, VGS is 0.5, VGS is 0.8, VGS is 1 volt, and VGS is 1.2 volt. On the different value of gate to source voltage, what will be the graph of ID versus VDS? Okay, I am just looking on that. Okay, so here it is, net listing and pending. Okay, you can check it here. Of course, you look that graph in lot of circuit designing and ID versus VDS. This is, and why it is showing that less slope, because you are using a higher length. If you are not using higher length, if you are using a 45 nanometer, so it will be showing that lot of channel length modulation effect. The lambda is high. Okay, so for reducing that, for providing the less slope, I am using a higher length, higher channel length. Okay, for a 45 nanometer. Okay, so here you have a, okay, so you can check it at 200 millivolt. It is that current is nearly 4.7 nanoampere. I can say that this is a cutoff current or sub threshold current, that is very small. And if you talk about 500 millivolt, that is also very small, that will be a sub threshold current, that is 4.51 microampere. But if you talk about 800 millivolt, because you know that VTH is 615 millivolt, okay, or any voltage of the VTH, okay, so you can check that VTH also. So this is your 800 millivolt. Okay, so you can, so this is your 50 microampere for what? For VGS is 800 millivolt. You can check it at 1 volt it is 105 microampere. At 1.2 it is 175. You can check it what is happening at 1 at this is at 1 volt. You find that your current is 107, or I can write it press V. So if you press V and you can check it at any point, you can find it, okay, at 867 millivolt. For 200 millivolt it is 5.8. For 500 millivolt it is 4.8. At 800 millivolt of the VGS it is 51. At 1 millivolt it is 108. At 1.2 it is 176. So you can check it, it is not double. It is just what, that 800 to 1, that have a difference of voltage is 200 millivolt only, but the current is changing in a double amount. Or you are looking at here that 1 volt to 1.8, the voltage difference is 0.2 volt, means 200 millivolt, but current is 108 to 176. This means 68 microampere is changing. Why it is happening a large amount of change? Because ID is directly proportional to VGS minus VTH ka whole square, that is square term. So that's why it is looking a small amount of change of gate to source voltage, a large amount of change on the output side. That's why it is showing that amplifier. Now, what is the meaning of amplifier? You are amplifying the signal. Now, okay, you are providing, okay, let I have a voice. Okay, my voice is not that much enough to listen you properly. That's why we are using an amplifier. Okay, so we have a voice, my audio, we amplifying that. So okay, that what will be that, okay, my voice convert to the electrical signal, means I am using some transducer from converting a audio signal to electrical signal. That electrical signal will be amplifying by the help of amplifier, and last side we are using just transducer from electrical signal to audio signal. Okay, so that is the process. Okay, just like the transmitting the data. Okay, so just why that amplifier is important. Okay, so here you can look at here why that saturation region is important. If you are talking about the same thing in a linear region, this is the linear region where this is that linear region. This is a linear region where you find it at 200 millivolt. This is 3 nano. At 500 millivolt, it's 3.4. At 800, it is 25 micro. One is 38. 1.2 is 48. Means that is not that much good. In a linear region, that is very small current and not providing that much effect. But if you are going for a saturation region, a small change of the gate to source voltage, you will find a large amount of change in current. Okay, so that's why. Okay, and that you can find that what will be the region. You can go for classic and you can check that browser, and in a browser you can simulate that, okay, where is the region. Okay, you on the basis of that you can check the region also. So here it is region. Okay, so the region is here. So I am just explaining one by one. This is for 200 millivolt. This is for 200 millivolt. This is what, that is region 3. It is always region 3. If you are talking about 200 millivolt, it is always showing the sub threshold region. If you are talking about 500 millivolt, this is a linear region. After that it will be in saturation region. This is a linear region. After that it will be in saturation region. If you talk about 800 millivolt, that VGS is 800 millivolt, that nearly it will be at 3 till 370 380 millivolt, it is linear. After 380 millivolt it will be in saturation. If you talk about VGS is 1 volt, for 1 volt it is make it linear to 590 millivolt, and after that it will be in saturation. So as per, if you are increasing your VGS, your overdrive voltage means VGS minus VTH. Of course, that VDS is equal to VGS minus VTH. That is called overdrive voltage. The minimum voltage on the drain you require to make that saturation region, or that is called overdrive voltage. The overdrive voltage of the MOSFET, it depends on the gate to source voltage and VTH. So if you are increasing your gate to source voltage, that means you require more voltage on the drain side to make that MOSFET in saturation region. That's why if you are increasing your gate voltage 500 millivolt, yeah, 800 millivolt, yeah, 1 volt, yeah, 1.2 volt, your overdrive voltage is shifting towards right side. Means you require a higher drain to source voltage. Okay, if you are lesser than VTH, this is always in sub threshold. There is no any requirement of, if VGS is less than VTH and it is not enough to greater than, so it is. So you can check it in such a way there. Okay, so or you can check that VTH also. If you are interested for VTH, here it is VTH, where it is VTH. So this is the VTH. You can check it. Okay, this is the VTH. So at 200 millivolt, 500, that VTH is same. You can take any value of that. This is the value. This is what that value is, 427 millivolt to 409. That 18 millivolt difference means I can say that that is nearly equal. But if you are using a higher length, your VTH is starting from 420 millivolt, 427 millivolt. Okay, the threshold voltage is 427 millivolt, and it is if you are changing your VGS, so that is not that. If you are changing your VDS, that is not affected. It is nearly about 409. That is at 80 millivolt change. That is okay. 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 So you can understand in such a way. Okay, what is your VTH? What will be effect? Okay. So that is why at 500 millivolt it is showing the saturation region. Okay, if you are using the length is small, so it will be is higher VTH. Okay, so use that. Okay, so I think it is enough for today. uh, we will continue this part. uh, yes dear, if the time is permit, we will work on the layout also. uh, Okay, we provide a complete analog and layout. Okay, sir, in this same concept applicable of flip flop. No, dear, digital, in a digital we never talk about the region. We in a digital we always talk about that switch on and switch off. Okay, there is no any requirement of linear saturation cutoff, and just only talk about cutoff means switch off, on means switch on. Okay, we never talk about that linear saturation or something like this. Okay, if you require the linear saturation, you can talk about the delay. Okay, uh, JK flip flop cause toggle state. How to solve this problem in transient analysis? In a JK flip flop, we talk about the switch on and switch off, and we use a RC concept here. Okay, we after today's class, in the next Saturday class, next class of the Saturday, so we will start that how that MOSFET is charging or discharging, where you can understand okay, what will happen, okay, of that toggling stage. Okay, and you can understand in the transient analysis. So in Saturday class we talk about the charging or discharging by the help of course, firstly we will discuss digital, then we will go for the common source amplifier or inverter. Okay, so I think it is enough for today. Thank you so much, everyone. We will continue on Saturday. Okay. Thank you. Thank you so much, dear. Bye bye. Take care.